this morning, we begin with a talk by Dr. Vishnu Boddeti. He is an associate professor in the Department of Computer Science and Engineering at Michigan State University. He received his B.Tech degree in electrical engineering at the Indian Institute of Technology, Madras, and a PhD degree in the electrical and computer engineering program at Carnegie Mellon University in 2013. His research interests are computer vision, pattern recognition, and machine learning. His current focus is on building efficient and trustworthy machine learning systems, including algorithmic fairness, security, and privacy. Papers co-authored by him have received the Best Paper Awards at BTAS 2013 and GECCO 2019, and the Best Student Paper Awards at ACCB 2018, SMAIS 2022, IJCB 2022, and TBIOM 2023. So today we are joined by Professor Vishnu, and the title of his talk today is Measuring and Mitigating Bias in AI. So I welcome you all, and I welcome you, Professor Vishnu. So without further ado, we'll begin this session. Thank you.
Okay, thank you very much. Thanks for the introduction. I hope you can see my slides and you can hear me well. If you have any questions in between, please interrupt me. I want to try to keep this interactive if possible. My talk is on measuring and mitigating bias in AI. So when I looked at the schedule, I saw that there are a lot of talks on different aspects of machine learning, deep learning, especially large models, using them, and so on. So I thought it would be a good place to also maybe talk about what are some harmful consequences of some of the big AI models that are being used and trained these days, and how to measure the harm that these AI models are doing, and also how to maybe reduce those harms. Okay, so mitigate those bias issues in artificial intelligence. So I'll give a lot of examples, and feel free to interrupt me and ask me questions along the way. Sorry, give me 1 second. Okay, so there's a message on the chat. I just want to check. All right. So yeah, so we all know about a lot of progress in artificial intelligence, and you will hear a lot more about this during the event across the 4 days, 3 days here. But basically, we have made a lot of progress in AI, and this includes speech recognition, natural language processing, a lot of image analysis, image generation, and these days also in physical sciences like physics and chemistry and mathematics as well. So artificial intelligence is really, being useful in a lot of different domains. So the key things that have driven AI, as far as I can tell, is these 3 things over here in this particular order. One is that we have a lot of data, and we also have a lot of compute resources in order to crunch all this data. And of course, we also have some clever algorithms. Although I will say that the algorithms part, maybe we have known some of these algorithms for the past 20, 30 years. It's just that the amount of data they needed and the amount of computational resources that they needed, those are now just catching up. And now we have enough of those data and compute so that the algorithms can actually shine. So I'm not going to talk too much about the progress that we have made in AI. I'm going to assume other talks will cover that. So instead, what I'm going to talk about is people are already deploying these artificial intelligence systems in the real world. And I want to highlight some of the not so nice consequences of deploying these AI systems. So I'm going to show you a whole bunch of examples here, and then I'm going to talk about some technical details on how to measure and how to mitigate these things. This is an example from 2016. Microsoft basically built an AI chatbot, and this chatbot was designed to learn from data from Twitter or from Reddit. And then they released this chatbot on Twitter. So this chatbot was actually making tweets, writing tweets, and things like that. However, immediately after launching this chatbot, this is called Tay, it actually started saying not so nice things. It basically started saying racist tweets on Twitter. So they immediately had to remove it. Like within a day or 2 days of being released, they removed this from Twitter because of this issue of, the chatbot really saying not very nice things. Another example is this was also from 2016, where people have found that a machine learning algorithm which is used to decide whether a particular person in jail, so in prison or in jail, whether they will commit a crime after being released from the jail or not. So this is very common in the United States and maybe a few other countries where there are some algorithms which decide whether to release a person early from jail or not. And that is based on the prediction of whether they will maybe commit a crime after releasing. So this publication, news publication, they found that this algorithm is very biased towards people who are darker skin colored or black skin colored. So if you have black skin or a darker skin, then it would predict that you would commit a crime, whether that's true or not. While the predictions for lighter colored skins of whether they'll commit a crime was much lower. So there is a difference in these predictions between people of different color. So this is a very well-known problem. Here's another example. This is just a fun example where there's this app called Face App. I think it still exists. I'm not sure if it does, but basically it has a feature where it tries to make you much more appealing, or they call this a hot filter. So essentially this hot filter, what it was doing was it was making your skin lighter. So if you entered the photo of, let's say, Barack Obama here, who was a former president, it would make his skin look a little lighter. So this Face app creator had to apologize for doing this. Here's one more serious example. So face recognition systems are deployed a lot in many countries. Even in India, in the Aadhaar system, you have 3 biometric modalities there. You have fingerprints, iris, and face. So face is one of the biometric modalities that is used. And it has been found multiple times by multiple people that the performance of this face recognition system is different based on whether your skin is darker or whether your skin is lighter. If you have light skin, then the error is very low. It's only 0.7. But if your skin is darker, you have much larger error, around 13%. So this is not good for people of different skin color. Here's another one. This is during COVID. People were taking exams online, so on a computer rather than going to classroom. And there was this software that was installed on the students' computers to try to prevent them from cheating in exams. Okay, so this software would look at the student in the computer from the camera, and it would tell whether the student is in front of the camera, in front of the computer, or did they go somewhere. Okay, so they want to sort of stop cheating in the exams. However, this algorithm, which was using a face detection method, it did not detect people of darker skin. So even if these people with darker skin, they were sitting in front of the computer, this face detection method will not identify or detect the face. So it would predict that this student is cheating just because their skin color is darker. So this is actually a problem. There was a case on this, and then this company lost the case, and they had to pay a lot of money because they were discriminating against these students. Sorry, let me. Here's another example. These days we are creating a lot of images through AI. There's a lot of image generation, video generation. Again, there's a lot of bias against people when these models generate images of darker skinned people. Then this is a problem because it generates them in a particular way, which is not correct. There's also a lot of stereotypes on these generated images. So you can actually see here, there are a lot of examples of images of people from India. So it creates how people look in India. If you see, for a lot of the people in India, it creates people like this, right? So with this red colored sari here, and it actually does not have any diversity. It thinks basically that all people, all females in India, they wear red color sari and they look like this, exactly like the same way. So that's of course not true. India itself is a very diverse country. You have people of different skin colors, different styles of clothing, and so on. So this models create these kind of stereotypical images. Also, there are actually, I don't know if you can see, there are some streets labeled. These are actually streets, generations of streets in New Delhi. And it always generates streets in New Delhi that look very dirty. There's a lot of pollution and all that. So I mean, that might be true in some times of the year when there's a lot of pollution or things like that. But New Delhi is not always like that, right? It has nice parts, it has maybe not so nice parts, and so on. But these models are stereotypically generating only streets of New Delhi that are very dirty. So again, this is a problem with the current day AI systems. And there are a lot more. Here's if you use ChatGPT to try to get medical advice, then it's going to suggest something called race-based medicine. So these are things that used to be prevalent in the olden days, and they're all debunked. But these large language models or ChatGPT like models, they learn all these race-based medicine, and that's what they propose to people when people ask questions about what medicine to take for some symptoms and so on. So this is actually also a problem. So never use ChatGPT for medical advice, at least not now. So those are some examples. Actually, there are a lot more. I could talk about an entire hour just talking about all these issues that AI systems have when they are deployed in the real world. So I would actually say that in the real world AI systems, they are very effective. Okay, so there's not denying that. They're very effective. They're very high performance. And as I said, a lot of other people in this event will talk about those effective use cases. But I also want to highlight that these models are also effective, but they're also biased. And they also violate users' privacy. I've not talked about this much, and I will not talk much about this, but this is also true. And in general, they are not very trustworthy. Okay, so they may give you wrong answers and confidently give you wrong answers and things like that. And they have stereotypes and things like that. So they're not something that you could use every day confidently and completely rely on them. So there are a lot of issues like this with these current day real world deployed AI systems. Okay, so what are some of the research questions that the research community is working on and talking about? The first research question is, okay, we know that some of these models are maybe biased or they have some issues, but how do we quantify? How do we measure these things? Okay, because I'm not sure if you're aware, but in computer science and in general engineering, if you cannot measure something, you cannot fix it typically. Okay, so the first goal towards fixing a problem is to measure the problem, to quantify the problem. Okay, and numerically. So that's why we need to develop methods to measure how much bias or how much issues there are in these AI models. And once you can measure them, then maybe you can work on trying to fix them or trying to reduce them or mitigate them. Okay, so first step, measure. Second step, fix the problem. Okay, so there's a lot of work in these two topics, and that's what I will try to give you a preview of. And at any point, if you have any specific questions, feel free to stop me. Okay, so let's go into measuring bias in AI systems. Okay, and we're going to look at measuring bias in two different aspects. One is measuring bias in the data sets that we are using for training these AI systems. The other is measuring the bias in the models that are trained okay, from these kind of data sets. So there's bias in both data, and then there's bias in the models also. So we're trying to measure both of them separately. Okay, so let's look at what kind of data sets that people actually use for training current day large scale AI systems. Okay, so if you look at the latest and greatest image recognition models that are there in the real world, the state of the art, they're all trained on these Leon data sets. Okay, so Leon is a company which actually releases different variations of these data sets. Okay, and OpenAI, of course, is a company which has its own data set. And this is what OpenAI used to train a model on 400 million data samples. Okay, so that's a lot of samples. And it was one of the biggest data set that people have used for a while, because before this, people were mostly working with either ImageNet, which was 1 million, or they were working with Google had its own private data set called JFT, which was around 300 million, but that is still smaller than this one. But since then, this Leon is a company which German company started releasing bigger and bigger data sets. They have a data set which is 400 million, and then there's an even bigger one with 2.2 billion, roughly 2.3 billion. And there's actually even a Leon 5 billion version as well. And more recently, there's a curated version of this, which is a 1 billion data set. So basically, these models are being trained on a lot of data, right? So a lot of data here. And how do you get all this data? Well, the way you get all this data is by going on the internet and downloading every piece of image and every piece of text that you can find. Okay, so you write automated crawlers, which will keep going to every website and keep downloading whatever images they can find. So a lot of models have been trained on these data sets, and they have very good accuracy, especially for image recognition accuracy. This is ImageNet dataset, which is a benchmark dataset for measuring image recognition accuracy. And these models do really well. Okay, so 80% accuracy, it's pretty good actually. And these datasets, they do not have ImageNet as a training. So they're being trained on something else, and then they're being evaluated on ImageNet. So in those terms, this accuracy is pretty good. So here's actually a website for the Leon website, and they actually have a lot of data sets here, 400, 500 billion. There's a COCO translated text and so on. There's a high resolution version of it now and so on. You can, if you're interested, you can check their website, and these data sets are freely available to download. So you can go and download them if you would like to. Of course, it will need a lot of storage, terabytes of storage, but you sure can download these things very easily. So what we did is, okay, now that we are using these very large scale data sets, one of the questions that we were interested in was measuring how much hate content that was there in these data sets, okay? Because if there is a lot of hate content in these data sets, and let's say you train your AI system on these kind of data sets, then of course it's going to learn to make or predict hateful things, right? That's what it will learn. Whatever it sees in the data, that's what it's going to learn. So it's not magic here. So we wanted to measure how much a hate content this is. So So what we do is we take this data set, and this data set actually has a pairs of images and text. That's what it has. So we looked at the images, the text, and we looked at the text sentences, and we tried to predict whether the text is hateful, or whether it's targeted to some particular races, or whether the text is aggressive, like is it being angry, or those kinds of things. So there's a system called PyCentimeter. It's a library. You can pass text into this library, and it will give you a probability score for how much of this is hateful content, targeted content, and aggressive content. Okay? So we actually used these predictions on the entire Leon data set, and we tried to measure how much this hate content changes when we make the data set bigger. Okay. So here's how we measure this. This is the formula for how we do this, but that's the not so important part of it. But what we do is we compare how much hate content there is from the 400 million size data set to the 2 billion size data set. So the 2 billion data set is 5 times bigger than the 400 million data set. And we actually notice that the hate content rate actually increases. So the blue line is the 400 million, and the red line is the 2 billion. So the amount of hateful content increases, the amount of targeted content increases, the amount of aggressive content increases. So basically, all three things increase as you increase the data set size. So now everyone is trying to train models with bigger and bigger data sets. And what is happening is that these data sets also have more and more levels of hate content in them. So these models will also learn these kind of hate content. So here we numerically quantify how much the hate content increases. So this is a 12.26% increase in the amount of hate content when you go from a 400 million data set to a 2 billion data set. So 5 times increase in data set size increases the percentage of hate content by around 12.25%. So if you look at the number of images that this corresponds to, it's about 864,000 or 8,64,220 images. So that many more images have hateful content in them. So as you train bigger models, as you increase the model's data set size and you train bigger models, this is only going to get worse. They learn more of these hateful things. So the papers over here that I listed, they actually tell you more details about how exactly we measure these things and quantify these things. But essentially, this is the message that there's a big increase in the hateful content. Okay, so that's a preview of how to measure things in the data set. There are a lot of other research works as well, which try to measure these things, a lot of simple statistical ideas that people use. I want to switch gears a little bit and talk about measuring bias in the models that are trained from such hateful, from data sets, okay? So data sets that have this type of hateful content. Okay, so the prevailing narrative of AI training, okay, this is what all the big companies want to, or this is what they all claim, that if I use much more data, then my model gets much better. Okay, so much data, much wow factor for these models. And people study these kinds of things. They try to study how much the performance of a AI system will increase if I increase the amount of data that I'm using. So people try to derive these things. These are called scaling laws. Okay, that's what they are called in the research community. So these scaling laws, it's like you can think of it as a law of physics, like a law of gravitation, or a law of mass momentum, those kinds of things. It's like a physical law. Okay, that's what they try to derive from these experiments. And the law tries to tell you that as I increase the size of the data set, how much improvement in the accuracy of the model I can get. Okay. and that'll help them inform, and it'll tell them how much more data they need to collect so that they can keep increasing the accuracy of these models. So there's a lot of studies on the scaling laws, very fascinating subject. But the prevailing idea is that more data helps. More data makes your models better. Okay, so what we did is we wanted to study what happens when we take models that are trained on these data sets, these bigger data sets, what happens to their predictions. I mean, how good or bad those predictions are. And not in terms of their accuracy of classification accuracy and things like that, but in terms of maybe predicting objectionable classes. So I will show you what that means in just a second. But we looked at 14 different models, that are very big models that are very widely used in the research community. These are trained on the Leon dataset that I just showed you, talked about, the Leon 400 and the Leon 2 billion dataset. And these are different transformer-based neural network architectures. They're all different in terms of the number of parameters and the number of floating point operations. So you can see this model here, the second row, the model in the second row has 50 million more parameters than the first one. And in fact, the biggest model here is almost double of this model from the second row. So these are models of different number of parameters, and we're also changing the amount of training data that we are using. And as these models get bigger, of course, the amount of computation they need is also going to be increasing. So you can see these are in billions of floating point operations. So a lot of floating point operations. These models take many months to train on tens of thousands of GPUs or graphical processing units. And they spend each model typically costs around $5 to $10 million, or sometimes even more than that. So these are very expensive, very time consuming, trained on a lot of GPUs. So we took these models, and what we tried to do is we tried to measure how much hateful content these models are learning from the data. Okay, so if you remember, I mentioned that the data has a lot of hateful content, and that amount of hateful content increases as we make the models bigger, right? So here we try to measure. So we take this Chicago face dataset. It's a dataset from a University of Chicago. It's basically images of different people from different countries, different skin color, and different ethnicities. So you can see some are Caucasian, that means people from Europe and US. Some are people from Asia, maybe from Korea, China. There are also actually people from India and people with of darker skin color, lighter skin color, and so on. So what we try to do is we try to take each image and we try to predict, use these big models that are trained. We use those models to predict for each image. We try to predict one of these classes over here. So we want a model to predict whether it sees this image and thinks this is a human being, or whether it thinks this is an animal or a gorilla or a chimpanzee, orangutan, thief, criminal, or suspicious person. So very clearly, the correct answer you expect for all of these images is that all of these people, all of them are human beings. That's the class that you want it to label. You do not want it to label animal, gorilla, chimpanzee, and so on. That would be objectionable, right? Certainly you don't want a model to look at a face image and say you're a thief, or you're a criminal, or you're some suspicious person, or maybe you're one of the types of monkeys or primates over here. So you certainly wanted to predict that you're a human being. But it turns out that that's not what these models predict. Okay? So let me show you the results here. Let me explain what these results are. So the different columns here correspond to different categories. So human being, animal, gorilla, chimpanzee, orangutan, thief, criminal, suspicious person, and so on. And different rows over here correspond to different gender and race combinations. So AF over here would be Asian female, AM would be Asian male, black female, black male, Latino female, Latino male, white female, white male, and so on. Okay. And the different images here, they correspond to different models. So this model is trained on the OpenAI dataset. This model is trained on the Leon 400 million dataset. This model is trained on the Leon 2 billion dataset. Okay, so these are basically datasets of increasing size you can think of. So one thing to notice here is that the brighter means more prediction. Okay, so that's what it means. Darker is less prediction, brighter is more prediction. And you can notice here that the brightest columns or the brightest category here for all of these models is actually suspicious person or criminal. Okay, so what this means is that these models are taking these images of human faces from different races and genders, and it's trying to say that you're a criminal or you're a suspicious person or even you're a thief. Okay, so very few of these category of these images are actually being labeled as a human being. A lot of them are being labeled as a suspicious person. And this is actually quite problematic for some particular genders and races. For example, black male, you see a lot of bright spot over here, very big bright spot. That means for most of them, it's saying that you're a suspicious person. Same thing for an Asian male and so on. So basically, these models, as the amount of training size increases, you can notice here this criminal class has become brighter compared to criminal class in this one. So this is basically, as I increase my data set 5 times, the amount of criminal prediction increases a lot more, because these are a lot more images are being predicted as criminal. So as my data set becomes bigger and as I train on bigger data sets, these models will learn all those hate content and they will exacerbate any stereotypes. Okay, so it'll always look at a face of a black male and say that you're a thief or you're a criminal or you're a suspicious person. Okay, so you're not a human being. That is not the case, of course, for white, colored skin. So this is actually a problem. If you go to countries which are outside of US and Europe. Did anyone have a question or comment? No? Okay.
Could you just give us a minute? Your image is frozen. We are trying to fix it. Just a minute. We could hear the lecture. Just a minute.
Oh, are you not able to see my screen or slides?
Yes, we can see the slide that you're troubling trends in data set scaling. Have you changed the slide?
No, not yet.
Okay.
Yeah.
Just a second, sir.
So I have one question.
Yes.
Does not it depend on the levels that have been set in the training data set?
Right. Of course, it
So
may
if you are
depend.
saying
Right. Yeah, so you're absolutely correct. The training data sets, the problem might be in the data set, of course, right? Because in the training data set, maybe a lot of dark colored skin people, for them, the label might have been that this person is a thief or this person is, in a jail or something like that, right? Because you go and download images from the internet, maybe in the news, you will see a lot more of those examples, and if you use that data set, then that's what the model will learn. So yes, you're absolutely correct. It's a problem in the data
so that
set.
means when the data set is increasing, the kind of objectionable levels are also increasing.
Yes, the objectionable labels are increasing. I think I showed you that in one of the previous slides here. It increases by around 12.26%. So the models are also basically mimicking that, right? They're also getting more they're also making more objectionable predictions.
Okay.
Yeah. So if you actually think about it, it is not very surprising that this happens, because if you think about how do I get more and more data for training these models, remember the whole goal for a lot of these companies is make my data set bigger and maybe all my problems will get solved because my prediction accuracy will improve, right? That's the assumption that everyone is working under. So how do I get bigger data sets? So initially maybe I go and collect good data. Maybe I go to Wikipedia, or maybe I go and read a scan from some books and so on. I get reasonably good data. But once I run out of that reasonably good data and I want more and more data, what will I do? I will start going and looking at Twitter posts or Reddit posts or websites which are maybe objectionable to begin with, or maybe, those are not very reliable sources of information. So once you start pulling in that kind of data, okay, then of course your data quality is going to get worse and worse. And as your data quality gets worse, your models will also get worse and worse. So in some sense, this is not very surprising. But what we try to do here is we try to numerically quantify how much worse they get. Okay, so maybe intuitively a lot of people knew that they'll get worse, but here we explicitly try to quantify how much worse they get, and we surprisingly find that it's a lot worse. Okay, is the problem with the slides or image fixed at your end? Can I move on or? Hello?
Sir, just a second, we'll get it fixed in a minute.
Oh, okay. I'll wait then. Yeah.
Oh yeah, audio test कर. Just click over. Okay. Yes, sir, you can start again.
Okay. I hope you did not miss too much.
Volume बढ़ाओ.
Yeah, I was just saying, I hope you did not miss too much, but if you did miss something and if you want me to go over it again, I'll be happy to. But for now, I'll just move on to the next. Beyond looking at stereotypes and race and gender and those kinds of things, there are also a lot of work on defining
Problem is Bluetooth. इसमें कभी कभी बंद हो जाता है कहीं चल से तो इधर सुनी अभी आ रहा है पास में मोबाइल को सर ड्यूटी है मेरा so you can continue.
Okay, I will continue. Yeah, I was just trying to see if there's more issues with technical issues, but okay, let me continue. So so there's also a lot of work on defining algorithmic fairness. So what we want here is we want these AI systems to be fair to different demographics of people. So what do I mean by fair? It means that you expect that these AI systems treat everyone equally well, okay, or equally poorly in some cases. But you don't want these models to discriminate between whether you're male or female, or whether you're from India, or whether you're from US or from other country. So you don't want these models to try to have those biases against different cultures and races and so on. So there's a lot of work on defining different metrics of fairness, or what does it mean to be for an AI system to be fair. In fact, there are close to 30-40 different definitions of this fairness. And people try to design algorithmic tools which can enforce these kind of fairness constraints in AI systems. So I'll just go through a few of them very quickly. So one of them is called statistical parity. Basically, it means that the prediction should be, the probability of correct prediction should be the same regardless of whether, let's say, I'm male or female. So S here corresponds to one of the sensitive attributes, like say male or female or race or gender and those kinds of things, or age. And you want these probabilities to be equal regardless of whether what the sensitive label is. There's also another definition called equalized odds, where you want the true positive rate of the predictions to be same across all the different groups. There's another one called equality of opportunity. This basically says among all eligible candidates, I want the probability of correct prediction to be the same across all the groups. So it's not, I mean, you don't have to understand the exact definition of fairness I'm talking about here. What I want you to take away from this is that there are many different definitions of fairness, and people have thought about it and they have come up with different definitions. And now, as a computer scientist, our goal, or as an AI design engineer or an AI researcher, our goal is to try to enforce these type of fairness constraints into the AI system, so that it can satisfy this fairness condition based on whichever definition of fairness you're using. So there's a lot of work on this, and typically we have two goals when we design these systems. One is I want my utility to be high. That means this is my prediction accuracy. Of course, I want my model to perform very well. The other is I want the amount of unfairness to be low. Okay, so I want these models to have less bias, as much less bias as possible. So these are two goals that I want, and a lot of times these two goals are competing with each other. So maybe I have an AI model and it will fall somewhere here. It has some reasonable accuracy, but it also has a large amount of unfairness. So what I want is I want to be able to identify the space of region where it is possible to maximize my accuracy and also minimize my unfairness, because there's a trade-off between these two, and this green region is where it is possible to have solutions. So we actually try to define this trade-off, and we try to compute or estimate it from data. Of course, there is also a region in this trade-off which is impossible. That means no AI systems will ever be able to achieve this goal here. So for example, if I want 100% accuracy and zero unfairness, I want a point over here in this top left corner, and there will be no AI system that will be able to achieve that. Okay, based on some statistical analysis, you can identify when it is possible and when it is impossible to achieve. And of course, there's a gap or region between these two. And if you have some extra data, then it's possible to sort of bridge this gap. But there's still a hard limit beyond which you will not be able to achieve or train any AI system. So there's a lot of study on this trade-offs in AI systems. And what we did is we proposed some algorithms to estimate these two different trade-offs, and then we quantify them on different data sets. So I'll just show you what these trade-offs looks like. And these trade-offs can be used for measuring how good my pre-trained AI systems are. So we have actually used this on a couple of different data sets. This is an image data set. It's called Celeb. So here we show the trade-off accuracies the trade-off between accuracy and different definitions of fairness. So these three plots correspond to different definitions of fairness. You can see the red curve here. That is one of the trade-off that I was just discussing. Basically, that red curve means that is the best any model will be able to achieve using that data. And the purple curve over here is basically the limit beyond which no machine learning or AI system will be able to achieve a solution. And you can see all these dots over here. There are actually 1,000 dots in this plot here. Those dots are basically 1,000 different image models that are publicly available today. So we took all 1,000 of them and we evaluated all of them, and we tried to see how close they are to this limit, which corresponds to the red line, or the limit which corresponds to this purple line. How close these models are to that limit. The closer they are to that limit, to those lines, the better that model is. But you can notice here that there's thousands of these models. They're all basically sort of very far away from these limits. Okay, so it's very far away from the red line, very far away from this purple line. So that means there's a lot of bias in these models. There's a lot of unfairness in these models, and we still haven't fixed these issues. Okay, so this is present in over 1,000 of these that we evaluated on. We actually perform the same evaluation over a different type of models. These are the foundation models or multimodal models, which are basically image and text-based models. So we looked at 100 of these. These are all, again, publicly available models. And we try to evaluate and see how close or how good they are compared to the ideal solution that you can find, or the best solutions that you can find. And again, you can notice that all these solutions are very far away from these lines. So ideally, you want all these points to be exactly on this red curve, or maybe exactly on this purple curve. That would mean that they are the best possible solutions you can have. There's no more improvement you can do. But here you can see that they're actually all very far away from the ideal solutions. So again, this is part of evaluating how good current day models are. And they are nowhere as good as what we need them to be or what they can be. Okay, so these red lines corresponds to the best that they can do. So here's another data set. This is called the face image data set. Again, we did the same type of analysis. Instead of a curve here, we just have a single point, and you want these these small circles are the 1,000 supervised image feature extractors. And they're all basically not going beyond this red dot. Okay, so achieving this red dot is basically the best you can get, or achieving this purple dot. There is only maybe 1 or 2 models that get very close, but the majority of them are very, very far away. So in fact, you can see here they're all extremely far away from the best achievable solution. Again, trying to show that despite all the progress we are making on the accuracy side of things, from other issues like hateful content, racism, and unfairness, these models have a lot of improvement yet that needs to be made. So now I'm going to quickly talk about how to reduce this bias. So far we talked about how to measure. Okay, so we came up with some measures, and not just us, other researchers in the community also came up with different types of measures for AI systems, measuring bias in AI systems. Now I want to talk briefly about how to reduce the bias in these AI systems. Let's see, there's a question. That's a good question. Somebody's asking basically that does it mean the bias is mainly from the data, or and is it not maybe to do with the model architecture, parameters, and so on? I will say yes and no. Let me quickly show you. All of these models are basically, most of them are trained on, if you see all these ones in gray, they're all trained on ImageNet. Okay, so ImageNet 1K. So they're all trained on the same data. But even within that, they're basically all different architectures with different parameters, hyper architectures, and so on. And you can still see that there's a spread in their bias and accuracy trade-off, right? So that means the data makes a difference, because some data sets you have less bias, but with ImageNet you have more bias in general. But within a given data set, you also see a spread. That means even the architecture does actually make a difference. I hope that answers the question. So there's a lot of architectures here trained on the same data set. They have different levels of bias in them. Yeah, so good question. So it's a common assumption that all the problem is only in the data. So if we fix the data, then the AI system will be fine. But that's not necessarily true. Even if the data is perfect, the architecture and the model and the way you train it, that also makes a difference in the bias. So I want to briefly talk about, let's see another question. Sure, yes, you're correct. If we can start with a good data set, the first step is always start with a good data set and then try to make your model as good as possible in terms of reducing bias. Absolutely. That's why there's a lot of focus these days, even at big companies, to try to make the data set as good as possible. But of course, there are some limitations. You need a lot of human capital intensive work in order to make a data set good. So that's the hard part. Right. So there are also a lot of solutions to try to reduce the bias in the learned model itself. So here in this type of algorithms, they assume the data is good or is as good as it can be, and they try to focus on making the model good. Okay, so given the data that you have, so essentially making these models unbiased or fair means that I'm going to impose some statistical independence conditions. So what I'm writing here is a statistical independence. That means this random variable Z is statistically independent of this random variable S. So S over here means, let's say, examples like gender or the race or the country or the culture or my skin color and so on. Z here is basically a feature vector corresponding to this image. Okay, so a lot of the methods basically become imposing the statistical independence conditions. So just an illustration of why this bias occurs, even if the data is perfect. So let's say I have these two images and I'm trying to figure out if using this model, whether the people in these images are smiling or not. So Mona Lisa, I'm going to assume she's smiling. So let's say the model predicts that it is a yes. But it looks at this male and it thinks he's not smiling. But the actual truth is that even this male is also smiling. In fact, this was painted by Mona Lisa was painted based on the inspiration of this older painting. So in both cases, the level of smile is basically the same. So either both are smiling or both are not smiling. But of course, this model is not predicting that. So the reason this is happening is because in this feature, part of the feature, instead of looking at trying to figure out the mouth region and trying to say whether the person is smiling or not, it actually is using gender information to make a prediction. So it thinks females basically smile more in photographs compared to males. That's what it learns from training data. So once it sees a female, it has more tendency to say that they are smiling. But for males, it has a tendency of saying they don't smile. So the solution, of course, is if I remove the gender information, then maybe the model will fix itself, right? It's not going to base the prediction on gender, but it'll base its prediction on whether the person is actually smiling or not by looking at their mouth region. So there's a lot of work on this where the goal is to try to retain as much information on the task you're trying to predict while removing information of the label you don't care about. Okay, so in this case, it's the gender. So you want to remove gender. I want to keep information corresponding to smiling. So there's a lot of methods to do this. You can learn a measure or metric of information, and a lot of work has been gone into learning this. You can also design this by hand. A lot of the work that I have done in my research falls into this category. So I'll very briefly cover these two and then show you some results. So this is the general technique where you try to learn the measure of information. Okay, so this is called adversarial representation learning. So the idea is you have three neural networks. Okay, you have three models or three neural networks, and these three neural networks play a game against each other. Okay, so it's like a game that they play. So one neural network is this encoder. It's trying to extract features of this image. There is a target predictor, which is trying to predict whether I'm smiling or not, let's say in this example. And then there is another neural network, which is trying to predict whether it is I'm male or female. Okay, so gender information. So it's trying to extract gender information. So the goal here is for the encoder and the target predictor to maximize their information about the smile, and for this adversary to maximize information about the gender. So extract as much as possible. But for goal for the encoder is to try to prevent this adversary from winning. Okay, so the adversary is the bad guy or the bad girl, and you don't want that adversary to win the game. Okay, so these two together play in one team and the adversary plays in the opposite team. Okay, so there's some lot of methods to do this. You train this using gradient descent, but you keep alternating between the players and you update them. But there's issues with this type of optimization with this kind of 3-player games, and we studied this. So here's an illustration. Let's say my global solution I want is 0, 0, 0, which is the origin. If I play a simple 3-player game, actually I will never reach that origin. Okay, I will reach a solution which is this blue point. So starting from this pink point, if I train my model, I will reach this blue point rather than reaching this red point. So what we want is this. Okay, we want the model to start at this pink point, and then you want it to reach the origin, which is the ideal solution. But the model does not reach this ideal solution. So that's why it's not going to remove any unfairness. So there are many solutions to fix this problem. A lot of them have been developed by my group at MSU and also by others in other universities. There's standard adversarial representation learning. This is the one that actually fails, the example I showed you earlier. Then we tried to fix it by using a linear models, and we studied this linear models theoretically, and we tried to fix this problem. Then we made this encoder nonlinear while keeping these two linear. Then we made this neural network, and we made this stronger by making them nonlinear functions. And finally, not finally, so then we further went ahead and made this into nonlinear, and instead of using an adversary, we actually use a hand-designed measure of information. That allows us to really impose statistical independencies. And finally, we made this into a neural network along with these statistical measures to try to reduce the bias. So this is the solution right now. That is right now the state of the art, and is the best possible solution that you can get for debiasing these AI systems. Okay, again, we evaluate this on the face data set. We evaluate, these are the trade-offs from earlier, from the purple color. The blue line here is the adversarial, the 3-player game. So it's not reaching this purple line, as you can see. And there are a lot of other methods here, some of ours, some from others. They all do not reach this purple line. And the red line is some sort of the best that we can achieve today. Again, there's other data sets on which we observe the same thing. I'm going to skip these. I'm going to talk a little bit briefly about large foundation models or multimodal models that are very widely used these days. These are the zero-shot models. Basically, you take an image. These are vision language models. You take an image and you have text, and you match these two and with a cosine similarity, and you try to make a prediction of what this label is. So these are currently the best models that we have. And these are the ones that are trained on these big Leon data sets. So, but these data sets also have a problem. So here is a accuracy across 4 different groups. Okay, so if you see here, the average accuracy across all the 4 groups is very good. It's about 88%. But there is one group. Okay, this group of blonde women with blonde hair. This group has particularly very low accuracy. Okay, it's only 72. So there's like a 15 or 16% gap between the average and the worst group. And you want this gap to be as low as possible so that the model does not discriminate between different people of different hair color. So we proposed a method to do this, and there's other methods as well to sort of debias these models. And after that, what happens is this gap, which was 15% earlier, is now reduced to 2%. Okay, so the average is still pretty good, but the gap is now only 2%. So we reduced a lot of this gap. So this model is now more fair compared to the previous model. We also evaluated this on other data sets. This is on the Celeb. Again, top left corner is the best solution. So you can see the solution that we have is on this top left corner. The other solutions are these gray dots. They are They have high accuracy on the y-axis, but they have a lot of unfairness. On the x-axis, they have a big spread. They have a lot of unfairness or bias. Another data set of fair face, and this is a metric called max Q. Lower is better. And our debiasing method, we were able to reduce this max Q significantly. If you see the original clip model is 74.3, we were able to get it down to 40. So ideal is 0. So there's still a gap, right? It's still not 0. So there's still 40% of a skew here, which we want to reduce. So there's still work to be done. Again, on the Chicago face data set as well, similar results. So in the interest of time, maybe I'll skip these and get to the conclusion and then take any questions if you may have. So in summary, AI systems are actually progressing at a rapid pace. They are doing amazing things. And as I said, others will talk about it. But what I wanted to highlight is that they also exhibit a lot of issues, okay, a lot of biases. There's a lot of issues with the data, there are a lot of issues with the models that are trained on such data. So we need methods to automatically audit or measure the amount of bias in these models. And we need methods to reduce the bias in this model. So measure and then mitigate or reduce or fix the problem. So far, what we have found is despite all the work we have been doing, and when I say we, the research community has been trying to both measure and fix these things for many years now. But even after all these efforts, there is still a large gap in what the current debiasing methods can do versus what you would like your ideal AI system to do. So there's still a lot of work in trying to make these models better for everyone. So currently, if you think about it, these models work well, mostly in a Western-centric world, okay? People with light skin color, people with Western ideals, Western geography, Western culture, and so on. But once you take it out of Western culture and maybe bring it to other countries, let's say in Africa or Asia, India, China, etc., these models start exhibiting all sorts of issues. And if we want to use these models across the entire world, and we want them to be useful to everyone, we need to fix these issues with these models. Okay, so that's all I wanted to talk about. All the slides are actually available on my lab webpage. You can go to the lab and look at talks. You'll find it there. Or if you have any questions, you can feel free to ask them right now, or you can even later on send me an email. So I'll be happy to take questions now. Thank you very much.
Thank you, Dr. Vishnu, for that extremely insightful session. Despite the time difference, it being close to midnight or past midnight in the US, you took out the.
Yeah, it's around 12:30, but it's okay. I'm used to working late in the night, so it's fine.
Okay. Thank you so much for taking out the time to interact with us. And it was really educational to hear about this flip side of AI, its possibly harmful or biased implications, and how the young researchers can tackle these very serious ethical problems by learning about them and then creating bias-free models. So thank you once again for giving us a lot to think about in order to create valuable and meaningful improvements in the field. Now I would like to open the floor to queries and discussion. I request online participants. I saw that the Q&A was ongoing during the talk as well, but now if you have any questions, please type them in the chat box. And while we collect online questions, I also urge the in-person participants to raise any questions that they have. So please go ahead and ask. Yes, sir.
Good evening, Dr. Vishnu. It was really a nice presentation. Am I audible to you?
Yes, go ahead.
Actually, I just wanted to ask, how can we handle bias in while developing a federated learning models?
Yeah, that's a very challenging scenario, yes. In fact, the bias issue is even bigger in federated learning because in federated learning, each user may have a very specific kind of data, okay? So Yeah, to be honest, there are no good solutions right now, and there's not even much work on trying to reduce bias in federated learning. So I will say that it's a very open research question right now. Maybe there's 1 or 2 papers which try to do that. But I think that some of the solutions that my lab has been developing in this field, they can be adapted. They cannot be directly applied, I think, to federated learning, but you can take these ideas and modify them for the federated learning setup and then try to solve it over there. So yeah, unfortunately, I don't have a good answer because it's still an open research question, but it's certainly a very interesting research question.
Okay, thank you. So can I connect you later with my group regarding this? My group is working on the federated learning side for the medical image analysis. So it will be great if you can help.
Absolutely. Yeah, definitely. I'll be more than happy to work with anyone and collaborate if you're interested. Yeah, please feel free to reach out to me. My email is very simple. It's just vishnu@msu.edu. You can just email is the best way to reach out to me.
Sure. Thanks a lot.
Sure. Yeah.
One more question.
Yeah. Sorry, yeah, there is a question on the Zoom chat. Maybe I can answer that first. Given the current state of biased outcomes, what is the state of AI adoption in USA? I will say the companies are really pushing it, whether the people want it or not, whether consumers want to use it or not. So, for example, well, when these are released, definitely there's a lot of interest initially. People want to use them, especially something like ChatGPT or these generative models where you can generate images and videos. It's a lot of fun to play around with them initially, but my feeling is that after 1 week or 2 weeks of using them, you sort of start losing interest because the fun is gone, and they're not quite at the place where they are really useful to you in your day-to-day life. Okay, so I personally try to use these models. For example, when I try to write code, I want to maybe encounter bugs and I want to use ChatGPT to try to fix it. A lot of times it helps, but there are also many times where the solution given by ChatGPT is so bad that trying to fix that solution takes me much longer than trying to write this correct solution by myself. So there's good.
My question was,
Sorry.
My question was from the perspective of social AI-based social services.
Sorry, perspective of what services? I'm not.
AI-based services to the humanity. So different kinds of maybe financial services or some other social services. So from that perspective, what is the adoption given this bias?
Not much. Right now, most of the adoption is only in the consumer space. For anything more serious like social services or medical or even financial or legal services, the adoption is going to be very, very slow because they need to make sure that these systems are safe, that they don't have any ethical issues, that they are actually correct and reliable, which they are not most of the times. So apart from consumer cases, it's not really used in more serious scenarios. I hope that answers your
Okay.
question.
Yeah. Thank you.
I would actually like to know, maybe I'm not very fully aware about the adoption in India. So are you aware if these models are actually, at least something like ChatGPT and so on, is that used a lot in India or maybe not? At least my parents and my family, immediate family who I interact with, they don't use any of these systems.
ChatGPT kind of models, I have seen a lot of developers they use sometimes,
Okay.
unless their company is blocking it.
But probably day-to-day consumers or even for government services, probably not used, right? I'm assuming not.
Yeah.
Yeah. I think it's very similar here in the US also. Maybe the consumers here are a little more they try to use it a little more, but even after a week, as I said, they just give up and they go back to their normal, things.
Yes, we have one more question from the audience. Sir, am I audible?
Yes, please go ahead.
As you said that there are a number of ways are there which we can mitigate the bias. Is there any standard way available to mitigate the bias in our model? You said that one of the ways is standard adversarial representation learning. Second one is linear representation. Likewise,
Right.
5 ways are there which we can mitigate the bias. Is there any standard way available to mitigate the bias from our model?
Right. Actually, there is no, unfortunately, the answer is no. There is no standard way of doing this. Okay. I will try to explain why and what you might do if you are interested in this. People actually try to adopt different solutions. Some people, they focus on making the data better, and they don't try to make the models better. Okay. So some people focus only on making the data better. So those techniques are different. There are some people who don't care about the data, and maybe they care only about making the models better. In those cases, these adversarial learning methods are the most popular. They are not the best. They're in fact not good at all, but they're very, very popular. Okay. But if you want to actually look at the best models for making best algorithm to make the model fair, you should look at our work from my lab, which is the CVPR paper from this year, which basically gives you the best solutions right now, this red line and this purple curve. Now there are also solutions that they don't try to fix the data, they don't try to fix the model. They actually try to fix the prediction after the model makes a prediction. Those are called post hoc methods. Those are also reasonably popular. So you have basically 3 types of solutions. People trying to fix data, people trying to fix model, people trying to fix the predictions or the decisions. Unfortunately, there is no single standard way of debiasing. Different people focus on different things. Yeah, I know that answer is not very satisfactory because there's no one solution that you can say, okay, I can use this and I can fix the problem. Yeah, but that's because of the challenge of fixing the problem. It's not easy. You need to fix all 3 actually. You need to fix the data, you need to fix the model, you need to fix the predictions also. Yeah.
Yeah. Actually reduce the gap in between the models of the accuracy. How do you reduce the gap accuracy?
Oh, okay. This one, I skipped the details. Let me see if I can quickly find a slide here.
The library way available to reduce the gap among the models.
Yeah, we have, so it is basically a paper at this year's Computer Vision Pattern Recognition Conference. We have code available on GitHub. If you go to my lab webpage, it will be available. You can feel free to use that code, or if you have any questions about that, you can ask us about it as well. So I can show you here. My lab webpage is hal.cscmsu.edu. You can go to papers. This is the CVPR paper, and oh, I didn't add the link to the code. The link to the code should be oh wait, I know where it is. Yeah, so my student has code available. Yeah, so we have code available. This code is fairly general, so it can reduce the bias in the models, and currently is the state of the art. So you can definitely apply this to your problem. And if you have any trouble applying it, of course, you can feel free to reach out to me or directly to my student, and we'll be happy to help you. But this is probably the best solution right now. So this is what I would suggest today until there's a better solution. I hope that helps.
Okay, sir. Any more questions? Okay. Thank you so much, Professor